It's, of course, a great honor to speak at this conference in memory of our dear friend and colleague, Jean-Pierre. I met him about 15 years ago when I was a PhD student still, and he was a really a giant in the field and a really kind-hearted and a very, very nice person. I really miss him very much. So especially remember many trips here to Grenoble, even with my family, to visit him. It was really beautiful. So, so my talk would be rather algebraic, so more on the algebraic geometry side, and it's joint work with Simion, Filip at U Chicago and John Lesieutre at Penn State. So X will be a smooth projective variety over the complex number. Of course, as some of you know, I'm a more analytic-minded person, so secretly you can think of a Compar-Kähler manifold here, but the talk will be basically just about projective varieties. And D will be a divisor on X, so Cartier divisor for now. And again, if you're more analytic-minded, you can think of D as being replaced by a 1-1 cohomology class, but not necessarily. So the key ingredient or the key definition of the talk is the volume of D. So this, I'll call it vol, is a lim sup when, let's say, n goes to infinity of the space of sections of and D, sorry, that's M and D. So you look at how fast the space of global section grows compared to the fastest possible growth, which is m to the n, and you normalize by you put a factorial normalization factor, and this lim sup turns out to be a non-negative real number. I mean, it's obviously non-negative, but it's not maybe not totally obviously finite, but it is, and what it does is exactly what's written here, measures how many sections you have for large powers of D compared to the largest possible growth. So I'm not quite sure where exactly it was introduced formally, so maybe don't put me, but certainly a good reference is Rob Lazarsfeld's book. Probably appeared implicitly in some earlier work. So it has a lot of nice properties, which you will find in the book. So first of all, if D is an F, which in the algebraic setting means that it intersects non-negatives with all curves, then the volume is just given by the self-intersection divided by this n factorial factor. So that's a simple consequence of that. Oh, yes. Thank you. Thanks. Thank you. So this is a simple consequence of Riemann-Roch, or asymptotic Riemann-Roch. And the point is, yes, up to F. I think the point is that it's called volume because when D is ample, and you can pick a Kähler metric in the cohomology class, C1 of D, and then this number is really the volume of the manifold using that Kähler metric. So that's, I think, why the name volume. And more properties, this lim sup is actually a limit. I believe this is a result of Fujita, so the lim sup is a limit. And importantly, it's a numerical invariant. So if you have two divisors that are numerically equivalent, so in this algebraic setting, that means the intersection with all curves are equal. Or if you're more analytically minded, it means equivalent that the first-gen classes are equal in the RAM cohomology with the real coefficients. Then the volumes are the same. So it's numerically invariant, and therefore it descends to a function on the space of divisors modulo numerical equivalence, which is denoted by N1X, the Neron-Severi group. So these are just the divisors modulo this numerical equivalence, which is a finite dimensional vector space, actually a abelian group. so finite rank abelian group. And also has a nice homogeneity property. So if I say do k times d, I get k to the n vol d. So because of this homogeneity, it means this implies that you can naturally extend it to q divisors. So vol naturally extends to q divisors. Oops. By clearing denominators, and this property tells you that no matter which way you clear denominators, you always get the same result. And so again, you get a volume function on the Neron-Severi group tensor with Q, say over Z. So on the rational Neron-Severi group. And importantly, Rob here proved that this function that you get is locally Lipschitz. So this is locally Lipschitz. And so once you have a local Lipschitz function defined on this Q vector space, you can extend it uniquely by continuity to a local Lipschitz function on the underlying real vector space. So you get continuous extension vol on the real Neron-Severi group. It's just this tensor with R. So this real Neron-Severi, oops, of R divisors modulo numerical equivalence. So divisors. Okay, so this is the object we want to study. And this is still locally Lipschitz because this one was. So locally Lipschitz. So now I have a locally Lipschitz real valued function, non-negative, defined on a finite dimensional real vector space. And that's what I want to study in this talk. And so these are all the basic properties that I need, I think. And the definition is the divisors, or RQ divisors, for which this lim sup is strictly positive, are those for which the sections of some multiples grow as fast as possible, comparable to m to the n, and these are called big. So D, if I just write D from now on, I suppose it would be an R divisor. Hopefully it's not too confusing. So D, so R divisor, is, again, if you're more analytic minded, you can replace D in your mind with a 1-1 cohomology class. And the whole story was extended by Sébastien Boucksom to a volume function defined on H11 with a real coefficient that extends this one. So there is a whole transcendental version of this, but it will not enter this talk, which is purely about, in some sense, counterexamples so in the algebraic domain. So anyway, D is called big if the volume is positive, which for integral divisors just means that this grows at least like a small positive constant times m to the n for all m sufficiently large. So you have plenty of sections. And the big R divisors form a cone inside of there. So B or Bx, Bx, these are just all the D. Okay, R divisors, modulo numerical equivalence. So I will probably, unfortunately, blur a little bit the distinction between R divisors and R divisor classes. If it's too bothersome, please complain. So D in N1 XR, such that vol D is positive. So that's N1. So this is a nice open convex cone, the big cone. All right, so you have this nice open convex cone, and inside this finite dimensional vector space, and the volume function is just 0 outside, 0 on the boundary, and it's strictly positive inside. So positive here, and then 0 outside. All right, so the simplest example which is actually useful for this talk, is the blow up of Pn at one point. So blow up Pn at one point. So here you have a map pi to Pn, and the E is the exceptional divisor. Then the Neron-Severi group of X is easy to describe. So N1 XR is two-dimensional, and it's generated by, for example, the pullback. So H is the pullback of the hyperplane bundle on Pn, and the E, which is just the class, Chern class of the exceptional divisor of E. And so numerical classes of those, and the big cone can be described, again, it's in Rob's book, as all the classes of the form, say, XH. It's more convenient to flip a sign, so minus YE, so instead of plus, because now you can just say the X is positive and Y is less than X. So these are the inequalities that define the big cone. So one second, let's try. It's okay, more? No, too much? It's okay, I guess. And you can draw the picture in the H and minus E variables. The big cone is this part. Yes, again, picture taken from Rob's book. And the volume function of this X H minus YE is equal to X to the n minus Y to the n, or X to the n, according to whether the Y component is non-negative or strictly negative. So here is xn minus Y to the n, and here is x to the n, separated by this wall here. So the function, the volume function in this example is piecewise polynomial, you could call it, yes. And there is this discontinuity of the second derivative when n is equal to 2. So when n is equal to 2, the second derivative is discontinuous across this wall. All right. OK, so let's go here. So the motivating question or theme of the talk is the same as the title. What is the regularity of this function? And just regularity in the sense of real analysis. In the sense of real analysis. So certainly, we do know that on Neff classes, sorry, it's written up there, on Neff classes, the volume is just the self-intersection. That formula is true also for R divisors. And that function is indeed a polynomial function, so the best you could hope for. So on an F cone, so vol is a polynomial on the cone of Neff classes. I mean, there will be Neff R divisors in this N1R. So the Neff cone does not either contain or is contained in the big cone. So I don't really draw the picture, but in general they have the different positions, but they do intersect non-trivially in the ample cone at least. So in the ample cone, which is inside Bx, the volume function is definitely a polynomial. And outside, there is this very nice result of Lazarsfeld-Mustata and Boucksom-Favre-Jonsson. From some years ago, I think around 2009 or 2007, 8, so something like that, that the volume function is C1 regular on the big cone. So it's differentiable, and the first derivatives are continuous inside this open cone Bx. And in general, just by this example here, when n is equal to 2 here, in general, it cannot be better than C11 on Bx. Cannot be more regular than C11, which means that the second derivatives are bounded, but they may not be continuous. Exactly like this example when n is equal to 2. So this is the best you could hope for sure. In fact, it's certainly a very interesting question whether this is actually true in general. So is it always true that volume is C11? If you want, you can say lock. I don't mean that you have a global C norm bound in Bx. This would definitely be true if it was true that the volume function is piecewise real analytic. For example, if you have a locally finite decomposition inside the big cone where the volume is real analytic on each part and continuous, then since it's C1, it would follow that it's C11. And certainly in all known examples where one can compute the volume, it is always piecewise real analytic. And it is not always piecewise polynomial. There are examples where it's given by something like a square root. There are examples where it's given by a transcendental function like log on some of these chambers. So that's definitely a challenging question. So our talk, however, is about what happens at the boundary of the big cone. So this talk is about regularity of vol at the boundary. And in fact, more precisely, regularity along some very, very special segments. More precisely, about the volume of D plus, I don't know why I call the parameter S instead of T. So let's stick to my notes, but maybe T would have been better. Of D plus multiple of A, where S is a real number, A is ample, and in fact will be sufficiently ample in most of the discussions. And D is always going to be on the boundary. So I will take, the picture is there, but it's out of reach. So I put it again here. So our D will be an R divisor in general on the boundary. So because it's on the boundary, the volume of D is 0. That's the same thing as being on the boundary. And then you move a little bit inside. So A is ample when S is positive. Let's take it positive. If S is negative, this is just the zero function, so not interesting. So if S is strictly positive, this is ample, and this is on the boundary, and it's easy to see that ample plus so-called pseudo-effective is big. So you are immediately inside the cone. So this would be D plus SA, S strictly positive, something like that. And now you are testing in some sense, the vanishing order of the function at S equals to 0. So S maps to this. S is going to be in, I don't know, let's say 0, 1. As I said, the negative values of S are not interesting. You just get 0. And this one, maybe sometimes I will call this f of S for shorthand. And so f is just a function of one real variable now. So it's a function from an interval to the non-negative real numbers. So it's a calculus type function from one variable, and you want to know what is the regularity of this function. So the question is, what is its regularity? So this was definitely inspired by conversation with Rob Lazarsfeld here. So what is, again, easy to say is that, of course, if your point D, by the way, sorry, I didn't say it, the closure of the big cone is called the pseudo-effective cone, pseudo-effective. So R divisor would be pseudo-effective if its numerical class is in the closure of the big cone. Analytically, it means that its cohomology class contains a closed positive current. And the terminology probably would be useful to have. So the easy case is, of course, when D is Neff. So if D is Neff, and you add a positive or non-negative times ample, you are still Neff. So these are all Neff for all S non-negative. And the volume for Neff is just a self-intersection, which is just a polynomial. So then D plus SA is also Neff for S non-negative. And so this volume is just a self-intersection, something like that. And this is just a polynomial in S. Okay, so a polynomial, so it's a real analytic, yes, a perfectly nice function. Okay, that's encouraging. And however, so what, furthermore, you can easily see the degree. So what is the degree of this polynomial in S? So this polynomial, by my assumption, will vanish at S equal to 0. So it has positive degree. And the degree, you just expand out this self-intersection, and you look when D to the P intersection with A to the N minus P, when is that 0 or when is that strictly positive? And the first time when this is strictly positive is called the numerical dimension of D. So degree equal to the so-called numerical dimension. Oops. Of D, which is less than K, just the max of all this, sorry, the maximum of all the K, such that D to the K dot A to the N minus K, but that's actually the same as just when this self-intersection is not 0 in H2K. Mean. So it starts 0 the first time when it's not 0, so minimum, yes. And non-zero in H2K seems right.
That's not the degree, it's the lowest.
Yeah, sorry. So it's, yeah, you're right. It's not the degree. It's vanishing order, yes. Yeah, okay, I was about to write a formula, but there's no space. Anyway, yeah, so it's exactly. So f of S is equal to nu of D here. Is some non-zero constant, strictly positive times S to plus S to some higher power, or just say little o of S to the nu of D. Or if you want even big O, S to the D plus 1. Okay, it's overkill, it's just a polynomial. So anyway, it's, yes, not the degree, but the smallest non-zero term. All right, yes. What do I do now? Nope. This one down, then the other one disappears? Okay. So if I do this, no, that's bad. I was okay, okay. All right, yes, it's good?
You can also do the other one.
Yeah, do I move the other one? How to do it?
Try one of the lower right. Lower right. Yes.
Oh, yes, thank you. Very good. At the last attempt. I prefer the previous arrangement, I have to say. The fixed blackboard, but all right, so, ouch. Okay, so from this, you can say very simple case. A question was naturally posed. A question. So Brian Lehman and Thomas Eckel and others, is true in general that the volume is at least comparable to a monomial like that. So is it true that given any D, always R divisor as usual, do we have, so NA ample, does there exist some K, natural number, and C positive such that for all S in whatever 0, 1, we have that this volume of D plus SA is bounded above by constant S to the K, and bounded below by constant S to the K. So that's a much weaker statement inspired by what happens in an F case. So it has a polynomial type behavior at the C0 level. So sorry, I think this eraser could do a better job. Now the point is, in the papers of Lehmann and Eckel, this was actually proved as a theorem, but there were mistakes in both of them. So it became actually quite interesting to resolve this issue. And John Lesieutre, I think in 2019, showed that it's false. So no. So what he found, you have X, there exists X Calabi-Yau threefold. In fact, it's very explicit. It's just a general complete intersection in P3 cross P3 of type or degree, whatever you call it, 1, 1, 1, 1, 2, 2. So it's the intersection of three hypersurfaces with these multi-degrees. And this is a Calabi-Yau threefold by a junction. Take this sufficiently generic. And he showed that there exists such an X. In fact, a general one would work. And there exists a D on the boundary. So pseudo-effective R divisor, maybe I stress, with volume 0, such that this function goes like S to a fractional power or rational number power, namely 3/2. So there it is. Yes, for surfaces, okay. Yes, sorry, I forgot to say it. So you can use the Zariski decomposition, and then I think Seb Boucksom told me this argument many years ago, and it appears in a paper of my student McCleary, but yeah, it's not hard. Yes, it's okay for surfaces. Yeah, good question. Yes, and such that the volume of D plus SA, so A here is anything sufficiently ample, is comparable to S to the 3/2. So this was quite a surprise, and where this comes from, it comes from holomorphic dynamics. Namely, you have two projections to P3. So when you forget one factor and forget the other factor, so there are two projections to P3, so from X to P3. And these clearly have a generically degree 2 by these equations. And so they are ramified degree 2 covers, and they have birational covering involutions. So get, I don't know, tau 1, tau 2 from X to X, birational covering involutions. And if you compose them, so if you do tau 1, compose tau 2, you get an element, again, birational automorphism of X, which has a chaotic dynamics. So with a positive, what is called, first dynamical degree, and I'll call this a phi, has chaotic dynamics. And in fact, this divisor D is an eigenvector under pullback. So phi star D is lambda D, where D is the lambda, sorry, is the first dynamical degree, which is strictly positive. So this is off topic, so I don't want to explain the definitions. It's for people who are interested in dynamics, like Kwong here. So I think this maybe just say Dean Sibony, who developed the theory of this eigenvectors for birational. This is not a morphism. This phi has indeterminacies. In any case, it comes from dynamics, so it has a dynamical explanation. Crucially, it's an R divisor, but not an integral divisor. So this construction will not give you Z divisor. Yes, yes.
So is there an interpretation of the three halves in the dynamic?
I can say you will see it soon, but yes, yes, yeah, yes, yeah, you will see it soon. Yes. What we do? Sorry, before then. So this shows that this conjecture is only false. However, it doesn't seem too far in the sense that you do have a similar inequality with just not an integer here. So the revised question then, so this was in the paper of John and also of McCleary, as I said. Do we at least have this for a real number power, say? So same assumption, so given this D, oops, and does an A ample or sufficiently ample, does there exist some alpha real number, means strictly positive, and C, okay, no, negative if you want, such that well, actually strictly positive, this vol D plus SA C S to the alpha. So is it at least comparable to some real power? Or if not, or even weaker, does the limit when S 0 decreases to 0 of this log vol over S exist? So if you have the one above, then the limit exists and it's equal to alpha. So you could ask this as a weaker question. Somehow, does it at least asymptotically behave like S to the power alpha in this much weaker sense? Yes. So it seemed plausible enough, and we tried to prove this one, especially using that log vol is concave, which we thought would help, but in fact it doesn't. So, and then we teamed up with John and proved that this is actually false also. So the main theorem is the following. So there's an X, but in fact, again, it's very explicit. So it's, again, Calabi-Yau n-fold. So given any n bigger or equal to 3, and given X in P1 to the n plus 1, which is a general complete intersection. Actually, sorry, general hypersurface. Sorry, shit. Complete intersection. Hypersurface complete intersection 1 of degree 2 to 2. So it's degree 2 in each of the P1s. So this is n-dimensional, so xn, which is also Calabi-Yau by adjunction. So given n, given a general hypersurface of this degree, which is smooth, of course, there exists some D, again, as before. So R divisor with volume 0 on the boundary of the big cone, and such that the lim sup when n, same thing, S goes to 0 of this log vol is n over 2. So I will explain where this comes from later, but this is morally the same as this 3/2, although it's not the same example. But when n is equal to 3, they're both Calabi-Yau threefolds, and the same 3/2 happens, and the lim inf is not that, is 1. Is 1, and actually you can choose here instead of 1. You can pick any real number in this range. In fact, you get a different D. So you can put here, you can put any delta real number in this range. So if you're given any delta, doesn't have to be rational, you will find a D. The lim sup is always n over 2 for those and the lim inf is delta. Yes?
What is the numerical dimension of D?
Yeah. It's a bit tricky, so I will explain a little bit. The problem is that there isn't one canonical definition of numerical dimension. There's a zoo of many different definitions, which I will mention a little bit, and they're not equivalent. Somehow that's one of the corollaries of this. So the BDPP numerical dimension, which is the analog of this one here, when n is equal to 3 is equal to 1, it should be this round down of n over 2. However, I don't think we proved that it's equal. We proved that it's less than or equal, and when n is equal to 3, it's definitely equal. So the BDPP numerical dimension should be this one when you put 1. But in fact, it's a good exercise to actually compute it precisely. So when n is equal to 3, it's definitely 1, the BDPP. But the other ones of Nakayama are different. So I will say a little bit later. Yes. So, all right. So this one here definitely destroys this and destroys this also. There are actually a bunch of corollaries, especially about the original question of the regularity of this function of f. Maybe I erase, no, oh no, I guess I can do, I should be able now to do this. And then, no. Yes, okay. All right. Too much? Yes. Okay. I'm a pro already. Yes. All right. So the corollary about the regularity, I will mention later the numerical dimension. Corollary for such a D, here you have to pick the D with 1, not the one with a bigger delta. So if you pick a bigger delta, it doesn't exactly work. So you should choose the one with 1, which is the most pathological one in some sense. So for such a D, we have that the original function, this f of s, equals to volume of D plus SA. A is anything sufficiently ample, is actually C1 on the non-negative real line, but not C1 alpha, even on any tiny interval for any given alpha or epsilon positive. So it cannot be better than C1 for any small improvement on any tiny interval as long as it contains 0. So that's the best you can do at the end point. So it's the boundary regularity is C1 and not better. So I will mention that this part here is basically the Lazarsfeld-Mustata Boucksom-Favre-Jonsson plus epsilon. So I will not say more. Why plus epsilon? Because they prove C1 in the interior, and here I'm claiming there is C1 also at the origin. So you just need the epsilon more to check that. So the point is to prove this. So proof. So it's just a calculus exercise, so I can do it here. So you have this function f of s. So what do we know? F of 0 is 0. And we know that f is a monotone increasing or non-decreasing, whatever you want to call it. And f is C1. This is I just take for granted from this result. And first, so you want to study the regularity of the first derivative, right? So you can use the what is called intermediate value theorem. So a sec. So given any let's say S, I mean, suppose that it is C1 alpha for some epsilon and alpha positive, and given some S in this range, there exists some Xi in 0S such that f of S is equal to S f prime of Xi. So this is this intermediate value theorem using that f of 0 is 0. And also from the Holder regularity condition that you assume, f prime of c is comparable to f prime of 0, right, up to c to the alpha. And you can bound this by s to the alpha, because c is smaller than s. And now you just have to consider two cases about the value of f prime of 0. So if f prime of 0 is strictly positive, so I mean, it cannot be negative because it's monotone. So if it's strictly positive, well, f prime is continuous, so it's strictly positive in some smaller interval. And so f grows at least linearly on some smaller interval. So f of s, at least cs for some c positive and for all s small. Yep. And then this inequality, you now can take the log of this inequality and divide. So when you take the log, it's the same inequality. The log c becomes addition. When you divide, when s is small without loss, log s has the opposite sign, right? So you get log fs over log s less than or equal to log c over log s. Yes. And then you just take the limit, lim sup, when s goes to 0, lim sup, you get 1. Sorry, here I should, you just get 1, right? So anyway, it's less than or equal to 1. All right, and that's a problem, because the lim sup is n over 2, and n is at least 3. Okay, so, I mean, here is this power here, right? Sorry, when you take the log, you get 1 plus what I wrote. I mean, it was 1 plus log c over log s. Right, okay, so that's impossible. And so you conclude that the other case is true. So f prime of 0 is 0. By the way, by BFJ and LM, f prime of 0 is this moving intersection product d to the n minus 1. So f prime of 0 is 0. And then you can plug it into here. So you get that f prime is quite small. And you can plug this into here. We combine these two. You get that f of s is less than or equal than constant s to the 1 plus alpha. Yep. That's exactly the reverse of this with a different power. So when you take the log and divide, you get that the lim inf when s goes to 0 of log fs over log s is at least 1 plus alpha. And again, that unfortunately is a disaster because here there is 1. So you can see that at this step is important that you had the 1 and not another delta. Otherwise, same thing will work, but with a delta here. So box, right? So that's just the calculus proof that this condition gives you exactly the sharp regularity at the end point for these examples. And another application which is related to this numerical dimension business is to the sections. Now, when you have an honest integral Cartier divisor, of course, we already discussed the growth rate of section of MD, but it was realized, I don't know, I guess Nakayama, maybe probably earlier, that to obtain better numerical properties, you should twist this by A, where A is ample, or sufficiently ample if you want. The growth rate of this has much better numerical properties. However, I mean, in fact, it's a polynomial in M. I believe it's in Nakayama's book. However, this does not make sense for R divisors, right? So if I have an R divisor, I can't take sections, but I can fix it with round downs. Now you have to be a little careful with round downs because to round down, you really need an R divisor, not an R divisor class. Yes? So okay, so if you have an R divisor, you can look at MD and round down. This is well defined. And if you twist it by A, this was considered certainly by Nakayama. And he wanted to know what is the growth rate So Nakayama is this comparable to m to some k for all m sufficiently large or sufficiently divisible or whatever, and seemed again plausible, and he could prove it for Nef D. It's not obvious because it's an R divisor. There are these annoying round downs, but again, this is not true. So another corollary of our theorem. So take the D as above. So take the X and the D as above. So the one with the 1 and n over 2. Then if you take the lim sup, when m goes to plus infinity of this log h0 of round down over log m. So this, I just told you that you cannot do this because it's only an R divisor class. But in fact, it is not hard to prove that this number does not depend on the numerical class. So if you change D by a numerical equivalent D, this is the same. So here you can cheat. And this lim sup is n minus 1. And the lim inf is different. So lim inf is, again, this n over 2 of the same thing. And these two are not the same as long as n is 3 or more. So what it says is that indeed such I don't know, this function here, which has nice numerical properties, is not polynomial-like, definitely not, in these annoying examples. And you can interpret this as saying that certain numerical dimensions of Nakayama are not the same. Maybe I don't bore you too much writing down the formulas, but there is some numerical dimension which is basically this, and one which is basically this. And now you can see that they aren't the same. So this can be interpreted as saying that certain notions of numerical dimension do not coincide. So of Nakayama again. So Nakayama. So he introduced several notions in his book, again, do not coincide. So there was already, if you want the details, probably it's best you look at our paper. So there was already, that example of John proved that some of these numerical dimensions do not coincide, and this proves that more of them do not coincide. So they are really quite different. And the proof of this, I can cheating sketch it for you. Yes, yes. Oh, yeah, yes. Good question, yes. It's the same, it's n minus delta, yes, exactly. It's exactly the symmetric, n minus, you will see why actually, yes. Thank you. Yeah, it's n minus delta, yes. And let's see. No. Ouch. Yes. All right. No, not really good, but it's okay now? Yes. So I can give you the rough sketch of the corollary, and then I give some rough idea of the main theorem, and then that's it. So sort of proof of the corollary. So here we need to use, first of all, you use that X is Calabi-Yau, which implies that every, let's say, phi birational automorphism of X is actually a pseudo-automorphism, meaning it's an isomorphism in codimension 1, is isomorphism in codimension 1. It's a general property for k-trivial varieties, and this implies that you can pull back divisors, so phi star d well defined, and preserves sections and volume, preserves H0 and vol, basically by the Hartog's extension theorem. So you can pull back divisors by any birational automorphism, and the point is that these manifolds X have a huge birational automorphism. So the birational automorphism is computed by Cantao Guiso. So their paper is totally crucial input for us. So the birational automorphism, they also computed, by the way, the Neron-Severi group is Rn+1. This is one of the easier parts. And the generators are the restrictions of O of 1 from each of the P1 factors, right? Hyperplane classes. And the birational automorphism is a huge free product. Z mod 2Z free product n+1 times. And these Z mod 2s are generated by birational covering involutions, again, when you project by forgetting one factor. I mean, analogous to the previous one. If you project to P1 to the n, forgetting one factor, because it's 2, 2, 2, 2, 2, this is generically degree 2, you again have a covering involution, and you have n+1 of them, and each of them generates a Z mod 2, and if you choose the manifold generic, then you have no relations, it's just a free product. So an enormous group, and also they proved a stronger version of the Kawamata-Morrison Kohn conjecture for this manifold. Kawamata-Morrison Kohn conjecture holds, in fact, a stronger version even. For us, that means that, so it's not the precise statement, but it's the consequence that we use. So given any d, let's say big, there exists some phi in the birational automorphism in this free product, such that phi star d becomes nef. And since the volume is preserved, it's also big still. So you can generate all the but big cone by basically nef classes and the action of the birational automorphism group. By the way, the nef cone is a rational polyhedral cone, so that's the connection with the Kawamata-Morrison Kohn conjecture. And so that's the other key input for us. And that, by the way, there was also a key input in what I'm just erasing here of John. The Kawamata-Morrison conjecture also holds in the other example, and it's also needed to make this argument work. So the input there is the same. And so quickly, how does it work now? So you compute. So this is the cheating proof, but at least it gives you an idea. So you want to compare the H0 of this round down. All right, so initially you are in trouble, but now MD plus A is easily seen to be big because D was pseudo-effective. This round down may take you out, but you can take A sufficiently ample, it will swallow it. So this is still big. And now you can apply this Kohn conjecture consequence. You can find some phi, which depends on M, but without making it explicit. I can make this phi star of that nef and big. And the H0 doesn't change. And then once it's nef and big, you can do excellent Riemann-Roch exercise. So this is uniformly comparable to the volume of that. Actually, it's a very nice exercise. In particular, it proves a strong non-vanishing statement for these special manifolds. Namely, if you have a nef and big Cartier divisor on these manifolds, it's automatically effective. So this is a conjecture for general Calabi-Gauss by Kawamata, I guess. So here you can do it with Riemann-Roch because the manifold is explicit, and you can compute the Todd class by hand. And then now the volume doesn't change by phi, so I can definitely remove the phi here. And the volume, let's say it doesn't change too much under the round down. This is again cheating, but it's not hard to justify. When you round down, you're only going to change at most by, morally speaking, 1. And this A you can take quite ample. This justifies this step. And this one here, by homogeneity, is m to the n times the volume of d plus 1 over ma. Right. So now you have exactly your function, f of 1 over m. Well, I sort of told you that there is some sequence of S that goes to 0 for which it grows like S to the n over 2, and some other sequence for which, sorry, it goes to 0 like S to the n over 2, some other sequence for which it goes to 0 like S to the 1. In fact, you can arrange it so that that sequence can be comparable to 1 over integer. Maybe it's not M, will be mj, so some sequence of mj's. So you can make this oscillate. Again, you have to choose a subsequence, not the whole M, but this can oscillate between 1 over M and 1 over M to the n over 2 by essentially the main theorem or the proof of the main theorem. And so you see exactly that this, you get n minus 1 and n over 2 as powers here. So that's the cheating proof. And finally, I should tell you in 5 minutes how to prove this theorem. So go here. So the theorem uses dynamics, uses also hyperbolic geometry. Again, the input came from this Cantao-Guiso paper also. So Cantao, idea for the main theorem. So from Cantao-Guiso, they constructed a quadratic form. Q, Beer invariant quadratic form on this Neron-Severi group formed on N1X of signature 1N. So this quadratic form comes out of explicit ad hoc, and it's very important to have this explicit description of the Brownian automorphism in terms of involutions. It turns out that these involutions will act as reflections with respect to this quadratic form. So that's somehow the proof that it's invariant. And nevertheless, you get from this, you get a copy of a hyperbolic space. So you get a copy of a real hyperbolic space, Hn, not the complex one. So as a sheet of the hyperboloid of classes such that QVV is 1. This is the familiar picture of hyperbolic space as a sheet. No, it's not exactly, yes. It's not exactly the same as the big cone, yes. Yeah, yes. It's different, yes. And, but yes, so this sheet, of course, we take the one which contains some ample class, right? So ample classes will have Q positive, and you take the sheet that contains amples, and you can take then the quotient M, so Hn modulo this beer. This is actually a nice hyperbolic real n manifold, hyperbolic real n-fold of infinite volume, as long as n is 3 or more. I will always assume n is 3 or more. If n is equal to 2, you get a finite volume different picture. And it has also cusps. So the cusps have finite volume, but there are some infinite volume so-called funnels, the opposite end of a cusp. So I will draw some picture. 1 second, let me go up. And the point is that, 1 second. First of all, you can describe the fundamental domain, which is basically given by Neff classes in Hn. So here, fundamental domain for this hyperbolic manifold are Neff classes in this Hn. And the volume function descends because, as I told you earlier, the volume is invariant under the action of Beer. So the volume was defined on N1. So of course, you can restrict it to this Hn, and then it descends because it's invariant. So you get a volume function defined on this real hyperbolic manifold. So nu, so from M to R, the volume function descended to this M. And so the picture is, I don't know, you have some cusps, then some topology, and then some funnels. So this is the kind of a naive picture of this M. And when you have the key, sorry, I think I push it down too much, but the key, in 1 second, is that the paths that we're looking at, after you renormalize them to lie on this hyperboloid, they correspond to hyperbolic geodesics. So if you have this gamma of S, which is D plus SA, I need to make this have a Q equals to 1, right? I want to make it lie on the Hn, so I just divide it by the square root of Q of D plus SA, D plus SA. Yep, so this class lies on the hyperboloid, so it projects down to some point, and this is a hyperbolic geodesic on M, geodesic ray on M. The ray parameter, S goes to 0, you have to do an e to the minus t transformation, corresponds to the parameter in the geodesic should be minus log S, basically, or minus 1/2 log S. So it's a ray in that sense. And conversely, so hyperbolic geodesic rays exactly come from these segments up to normalization. So now what you need to do is to sorry, in 1 second really, compare the volume that we want with this new function. So you just, volume of D plus SA is equal to this Q, D plus SA to the n over 2 times this new function of gamma of S, right? So the n over 2 now comes from the square root. I hope that's a reasonable explanation where it comes from. And this one you can compute by hand. This is straightforward because Q is explicit. This is comparable to S to the n over 2. And now this new is all that you need to understand. And in 2 words, this new is, of course, comparable to O of 1 if the geodesic stays in the compact part of the manifold in a compact region of M. So if your geodesic ray spends a lot of time in the compact region here, spiraling around, then for that period of time, this nu is comparable to 1, and your volume is comparable to S to the n over 2. However, if you enter a cusp like this, you can do, again, a totally explicit computation. In the cusp, S blows up like t to the, S to the 1 minus n over 2 in a cusp. So in a cusp, you do an explicit computation, and it blows up. It goes to plus infinity. The new function blows up, and this gives you the growth rate S to the 1. So all you need to do to complete the proof of the theorem is to construct a hyperbolic geodesic ray that first stays in the compact part for a while, then enters a cusp for a while, then it comes back to the compact part for a while, then it enters maybe a different cusp for a while, and so forth. So this you can arrange by hyperbolic geometry. You have to be a bit careful, but you can do that, and that gives you exactly this D. D is the limiting point of this geodesic ray and the sphere at infinity. So, by the way, this D is definitely irrational. So I will close with the open problem. Can you find any of these pathologies for integral divisors? So find such pathologies for D, again, in the boundary of the big cone, but the Cartier divisor, so Z, integral divisor. So this should definitely exist. I don't think having an integral divisor will rule out all of this story, but these methods, dynamics inspired, will never produce for you integral pathologies. Somehow they are always going to be irrational. So you need some genuinely different idea, I would guess, to find this. But exercise for you. Thank you very much.